Hello everyone. Today we will be continuing our discussion of normal curves with an overview of some of their properties. So I have over here on the board an example of a normal curve. So there's a few things that are important to note about this. So first of all, a perfect normal curve is going to be completely symmetrical. And down right here in the middle, we have our axis of symmetry. It's going to look the same on both sides, just of course mirror image. And when we have a perfectly normal distribution of data, this axis of symmetry is going to correspond to our median and our mean. Those two are going to be equal with each other for a perfectly normal curve. Other key points on the normal curve: 0.675 standard deviation, so this sigma, that's our standard deviation. 0.675 of those on either side of the mean. We're going to have our quartiles. So Q1, that's our lower quartile, in other words, the 25th percentile. And then Q3 is our upper quartile, that's going to be our 75th percentile. So mean or median, both of those are the same, plus or minus 0.675 standard deviations. That's where our quartiles are going to be. We also have one standard deviation away from our mean on either side. We have what are known as the inflection points of the curve. Inflection points are basically just where our curve goes from being curved downward to being curved upward. So you could also refer to this as it goes from being concave down to being concave up. So this is what the inflection points are. They're located exactly one standard deviation away from the mean on either side. When we have normal data sets, we can make some generalizations about how far away our data is going to be from the mean. So because of the way these normal curves are shaped with this bell-shaped curve, most of our data is going to be concentrated close to the mean. So if we go out 1 sigma, or 1 standard deviation, either side of the mean, 68% of our data is going to lie in that range of between basically mu minus sigma to mu plus sigma. If we go out 2 standard deviations, now 95% of our data falls in that range. If we go 3 standard deviations out, now we have 99.7% of our data. So oftentimes when we have approximately normal data sets, we can approximate that 3 standard deviations away from the mean on either side is going to be our minimum and maximum, because almost 99.7%, that's almost all of our data, is going to be within 3 standard deviations of our mean. Related to mean and standard deviation, we have the concept of z-values or z-scores. And this is basically just telling us, for any data point, how many standard deviations is it away from the mean. So the formula that we use to calculate our z-score is this right here, x minus mu over sigma, where x is whatever value we're looking at. Mu is our mean. Sigma is our standard deviation. If we're given a z-value for something, we can also convert it to its original value by basically just a rearranged version of this formula, x equals mu plus z sigma. So say we have a system where we have an approximately normal distribution with a mean of 10 and a standard deviation of 2. And we have a data point somewhere that is x equals 7, and we want to figure out what z-score that goes with. So the way we would go about doing this is we would say z equals x minus mu, so x is 7, mu is 10, over sigma, which we said is 2. And this is going to give us a z-score of negative 1.5. So what this tells us is that our data point, x equals 7, is 1.5 standard deviations below the mean. So if it's negative, if our z value is negative, we're dealing with values that are below the mean. If it's positive, we're dealing with values that are above the mean. So next, say we have a data point that has a z value of 2.5. We'll use this formula right here if we want to find the original x value of our data. So x equals mu plus z sigma. Mu, we said earlier, is 10. Z is 2.5. And then sigma, sigma we said is 2. So this would give us an x value of 15. So an x value of 15 is 2.5 standard deviations above our mean. Thank you for watching, and as always, if you have questions, I am happy to help.